Hello everyone, my name is Lim Sun Yi and QUAH is my groupmate. And today we are going to share about the ordinary differential equation, commonly referred as ODEs. These equations play an important role in the mathematics and are fundamental in various fields such as physics, engineering, biology, and economics. In this video, we will explore what ODEs are, some key concepts and theories, and how they are applied in real-world problems. First, let's define what an ordinary differential equation is. It is an equation that involves one or more functions of a single independent variable and their derivatives. The primary goal is to determine the unknown function that satisfies the equation. In mathematics, the term ordinary differential equation is also known as ODE. And in other words, the ODE is represented as the relation having one independent variable x, the real dependent variable y, with some of its derivatives. For example, y prime, y double prime is respect to x. Differential equations appear in a wide range of problems in physics and science. They are used to model many of the phenomena that occur around us, and we need to solve differential equations to analyze those phenomena. For some simple examples of modeling using differential equations include the modeling and growing of diseases, describe the movement of electricity, describes the motion of pendulum or waves is used in also Newton's second law of motion and law of cooling. And now let us move towards the overview of ODEs. The ordinary differential equation is further classified into three types, and they are the autonomous ODE, linear ODE, and nonlinear ODE. Let's talk about the autonomous ODE. So a differential equation which does not depend on the independent variable x is known as an autonomous differential equation. And as for the linear ODE, if differential equation can be written into linear combinations of the derivatives of y, then they are called linear ordinary differential equation. This can be further classified into two types: the homogeneous linear differential equation or the non-homogeneous linear differential equation. And that's what we will be discussing later. And the third type is nonlinear ODE. If the differential equation cannot be written in the form of linear combination of the derivatives of y, then it is known as nonlinear ordinary differential equation. And so today our topic will be mainly focused on the linear ODE. So let us continue with the key concept, order and degree. The order of differential equation is defined to be the order of the highest derivative that occurs in the equation. So we have an example of d2y squared dx squared plus 3 times dy dx plus 2 times y equals to 0. So the highest derivative, let us see, the highest derivative will be d2y dx squared because we have derived the y for twice, right? So the order of this equation is 2 because we have the highest derivative that is d2y dx squared. And let's go on to the degree. The power of the highest order derivative provided the equation is polynomial in derivatives. For example, we have a dy dx squared plus a y equals to 0. So the square makes this equation has a degree of 2, and it is also a first order ODE. So this equation is a second degree first order ODE. Okay, Now let's go on to the theories and laws of linear ODEs. The existence and uniqueness theorems provide the condition under a unique solution exists for an ODE which given initial condition. This theorem is essential for understanding whether our solutions are valid and applicable. So, this existent unique theorem also states that an object having some required properties and whose existence has already been established is unique. In order to prove that this is true, we have to prove that no other object satisfies the properties list. And this diagram shows an example that uses the theorem. For linear homogeneous ODEs, the superposition principle states that if y1 and y2 are solution, then any linear combination of C1 Cy plus C2 Cy is also a solution. This principle is particularly useful in solving complex ODEs. The reduction of order method is a method for converting any linear differential equation to another linear differential equation of lower order, and then constructing the general solution to the original differential equation using the general solution to the lower order equation. In general, to use this method with an nth order linear differential equation. So for example, our original solution is the y double prime plus p times y prime plus qy. So we let y equals to y1 times u. So and then we differentiate it. We differentiate it and then we differentiate it the second time and we put what we get into the original differential equation. So we get a new one. And this is how the reduction of order method works.
Good morning, everyone. My name is Caucasian 299428. Now I want to talk about example of first order ODE. Firstly, to do about first order ODE, we need to identify the integrating factor. Second step, we need to multiply both sides of the ODE by the integrating factor. Step 3, we need to recognize that the left-hand side is the derivative of y e power x. Step 4, integrate both sides with respect to x. And lastly, we need to solve for y. For the second order homogeneous ODE, we need to write the characteristic equation and then solve the characteristic equation and lastly write the general solution. Sometimes we can use some special method to solve the homogeneous differentiation equation. For example, we can rewrite it in the form of x and y multiplied by dx plus s and y multiplied by dy. And we can also substitute y equal to vx and dy over dx equal to v plus x multiplied by dv over dx, so that we can get dy equal to v dx plus x dv. Here is the example of using special method. For this question, we can let y equal to ux and let it become to dy equal to u multiplied by dx plus x du. Next, we can follow by substituting y and dy in the given equation so that we can get the answer from the slide. Then we need to separating variable u and x by left hand side and right hand side. After that, we need to integrate in both the side so that we can get the answer. And lastly, don't forget to write is the general solution for the differential equation. Now I want to talk about application in physics. The most simple application is about simple harmonic oscillator. This is because when the simple harmonic oscillator vibrating, we can get some solution. To solve the solution, we can write the characteristic equation and solve the characteristic equation and write the general solution. What is the connection between solution and Tyrell's law? For only first order linear ODE, it only included existence and uniqueness theorem and superposition. Reduction of order method did not involve in first order ODE. This is because it only occur during second ODE and not directly applicable to this first order equation. From the superposition principle, we can get that y equal to yp plus yh equal to e power s divided by 2 plus c multiplied by e power minus x. For the second order ODE, we can get three types of theories. Firstly is Eston's and uniqueness theorem. For the second ODE, we can got if involving reduction of order method. From the reduction of order method, we can assume by y2x equal to ux e power 2x. By substituting y2 in the original ODE to find ux, this process would lead to finding y2x equal to e power x. To confirming the general solution, yx equal to c1 e power 2x plus c2 e power x. From the example of second ODE, we can got the r equal to 2, r equal to 1. For the corresponding independent solution are e power 2x and e power x. We can get the general solution is y x equal to c1 e power 2x plus c2 e power x. In conclusion, our main point is ordinary differential equations are closely related to its own theories and law. For example, superposition principle, reduction of order method, and lastly is Eston's and uniqueness theorem. Is used for the linear ODE is used the Eston's and uniqueness theorem to interpret its own properties. And ODE will also be used in our life. For example, simple harmonic oscillator in physics. He also has its own equation during his movement, and therefore ODE play an indispensable role in our life. That's all for my presentation and my partner Lim Xin Yi. Thank you.